I am Kawan Rupasinghe and welcome to my presentation on heterogeneous and ultra-heterogeneous computing architectures. In this video, we'll explore how modern systems combine CPUs, GPUs, and other accelerators, why it matters for performance and energy efficiency, and how it shows up in real-world devices like supercomputers and cloud platforms. So what is heterogeneous computing? Heterogeneous computing simply means using different types of processors in the same system. Instead of relying only on a CPU, workloads are split between CPUs, GPUs, and other accelerators. So the idea is that each processor type does the work which it's best at, which leads to higher performance and better energy efficiency. Why do we mix these processors? Each processor type has a unique strength. For example, CPUs are flexible and can handle general purpose tasks, while GPUs excel at parallel workloads like AI and graphics. On the other hand, FPGAs are reconfigurable, giving low latency acceleration, and custom NPUs or TPUs are extremely efficient for narrow specialized jobs. So, ultra-heterogeneous architectures. So ultra-heterogeneous architectures go beyond just CPUs and GPUs. Modern systems on chip like Apple's M series or Qualcomm Snapdragon also integrate neural processing units, digital signal processors for signal processing, and image signal processors for image processing. This allows efficient handling of everyday tasks like AI and multimedia within a single chip. So moving on to real-world systems, these architectures appear across many domains at present. Smartphones and laptops combine CPUs, GPUs, and NPUs for everyday use and AI features. Supercomputers like Frontier and Summit use thousands of CPUs and GPUs to achieve the exascale performance. And cloud providers like AWS, Google, or Azure offer FPGAs and tensor processing units for accelerated workloads, and even autonomous vehicles combine CPUs and GPUs to process sensor data and provide the real-time perception and control. So there are numerous benefits from these heterogeneous systems. They deliver much higher performance than CPUs alone, and they manage the energy crisis because they are more energy efficient, as they are specialized processors which consume less power for their tasks, and they are flexible, supporting workloads from AI to scientific simulations and even to real-time simulations. Everything comes with challenges. So some of the few challenges that are there in heterogeneous systems is that one of them is they are very complex. They often require CUDA or OpenCL, and data transfer between processors like PCIe or NVLink can be a bottleneck, and scheduling tasks across multiple processors is non-trivial. And at the end, the scale of supercomputers, cost and power consumption become major concerns. So moving on to the recent trends, recent developments show how the field is evolving. Intel's Falcon Shores and AMD's APUs tightly integrate CPUs and GPUs on a single package, which reduces data moment delays. And domain-specific accelerators like Google's TPU and Apple's neural engines are optimized for AI workloads. And on the other hand, supercomputers like Frontier, Aurora, and Lumi demonstrate advanced technology in heterogeneous designs at the exascale performance. To summarize, heterogeneous computing combines CPUs with accelerators like GPUs and FPGAs. And ultra-heterogeneous systems push further by integrating many specialized cores into a single system. These architectures are already powering our smartphones, supercomputers, cloud platforms, and, as I mentioned earlier, even autonomous vehicles. And going forward, we can expect even tighter integrations and more domain-specific accelerators. Coming to the end of the video, these are some of the key references from which I gathered information. Thank you for watching. From mobile devices to massive data centers, the future is built on heterogeneous systems.